Hello students, I am your lecturer Shanta Mukherjee hai. I welcome you all for session 3 on Unit 1 ARM Embedded System and ARM Processor Fundamentals. The topics covered in the previous session 2 are block diagram of embedded system hardware, AMBA bus protocol and embedded system software. So we studied what are the different hardware in a embedded system. The best one is ARM processor core. Next we studied the important block controller. In that we studied two types of controller, memory controller and interrupt controller. The interrupts are handled by the interrupt controller and the memory devices are controlled with the help of the memory controller. Then we studied the types of peripheral devices connected to the ARM processor with the help of the bus. The different types of bus we studied. So there is a bus, AMBA bus protocol, the advanced microcontroller bus architecture protocol. In that we studied three types of AMBA bus protocol, ASB, ARM system bus, APB, ARM peripheral bus, and AHB, ARM high performance bus. These things we studied under AMBA bus protocol. Then we studied the different software components of the embedded system. So they were listed like the application in the top and hardware device in the bottom. And there is one important block initialization code which is executed first always. Then to connect the peripheral devices, we need a device driver. So all these things we studied in a embedded system software in the previous session. So in today's session, I'm going to cover the topics von Neumann architecture versus hardware architecture and ARM architecture families and ARM data flow model. ARM processor is a 32-bit high-end application. So for high applications, it is used. It uses load store architecture, important feature. So load store architecture, there are two types of instructions in ARM controller, load instruction and a store instruction. So what does the load instruction do? The load instruction copy the data from memory to register in the core. So loading from where to where you should understand. Loading the instruction from memory. So the instructions are stored in memory. So if you want to move it to the register, load instruction should be used. So the load instruction copy the data from the memory to the register. So the data is always stored in a memory. So this data is copied to register with the help of the load instruction. Store instruction copies the data from register to memory. Reverse. It stores the data into the memory. So if I ask you the question, if you want to store the data in memory, so where the data is moving from? Register to memory. Which instruction you use? Load. Load instructions move the data from memory to register. So if you want to move the data from register to memory, so where the data is going from? Register to memory. So it is store instruction. Load means loading data from memory. Store means storing data into the memory. Then there are no data processing instructions that directly manipulate data into the memory. So like memory to memory transfer, such type of instructions are not available in the ARM processor, ARM controller. So you have to move the data from memory to register or register to memory. There is no instruction to move the data between memory to memory. So data processing is always carried out in a register. The last point, data processing is always carried out in registers. These are the important points you need to remember in a ARM processor. So ARM processor, it is a 32-bit processor. Let us study the von Neumann architecture. Here, you look at the diagram here. There is a CPU and one block I have written and marked it as program memory and a data memory. It means that the program is stored, the code is stored in this memory, as well as the data is also stored in the same memory. and there is one bus communicates between CPU and a memory. So it has a single memory. There is how many memories I have shown here? Only one memory. So what it does, it stores both instructions as well as a data. So program is stored as well as a data is stored. The program and data memory put together and having a single bus connecting the CPU and memory. Both program and data, they are in the same memory and they are connected to CPU using this bus. So we provide the address from CPU to the memory to fetch the instruction as well as the data. If the CPU wants to fetch the instruction, so it gives the address on the bus, fetches the instruction. Then if the CPU wants to the data is also carried out on the same bus. It means the program as well as data, they are transferred to CPU on the bus. Both program and data memory is connected to the CPU by the same address and a data bus. Hardware architecture. Look at the diagram here on the right side. So you have hardware architecture. CPU is in middle, program memory on the left side, data memory on the right side. So look the above diagram. Program and data memory, there is a single memory here. But in hardware architecture, you have memory, separate memory for program, separate memory for a data, and CPU is in between. If the CPU wants to access the instruction from the memory, it takes the instruction from the program memory. If the CPU wants the data from the memory, it gets the data from the data memory. So both the data memory and program memory, they are connected to the bus. So this bus is a 16-bit size or 14-bit size or 12-bit size. So here the data is 8-bit size. It is shown in this diagram. But in our processor, the size of the width of the bus changes. So I'll tell you in the next session. Program memory different from that of data memory in hardware architecture. Both volatile and non-volatile memories are involved here. So volatile and non-volatile. Volatile means when the power goes off, the data will be erased. The data will not be retained. Such type of memory is called as volatile memory. Non-volatile memory, when the power goes off, the data will be retained in the memory. Such memories are called as non-volatile memory. If the data is retained after, even though the power is not there, the memories are called non-volatile memories. If the data is not retained once the power is not there, such memories are called as volatile memories. So both the memories are involved in a hardware architecture. This is done to increase its efficiency as both memories are being used. Since the program memory is different and a data memory is different, definitely the efficiency increases. In the upper case, in the previous slide, so since the data and program and data both are stored in the same memory, so if the CPU wants instruction as well as the data, it cannot do. So one at a time it can do because there is only one memory here. So because of this, the efficiency decreases. But in hardware architecture, the efficiency increases because it has got both program memory and a data memory. So this is all done to increase its efficiency as both memories are being used. It has two distinct buses connected to CPU. So it is connected, two buses are used here. So see the in one number, only one bus is used to access the data and the program. Here the two buses are used to access the program memory as well as a data memory. So ARM has different families, ARM7, ARM9, ARM10. ARM7, see the features of ARM7 here. It has three pipeline stage. So what is pipelining? The process of fetching the next instruction when the current instruction is being executed is called as a pipelining. So the three at a time, when suppose if we fetch the first instruction, in the next clock cycle, the first instruction is decoded, the second instruction is fetched. In the third clock cycle, the first instruction is executed, second instruction is decoded, and third instruction is fetched. All these things takes place simultaneously and they are called as a pipelining. So how many stages are there in ARM7? fetch, decode, execute. It supports high code density and low power consumption. So in ARM processor, so we are going to use this version ARM7. So we already know what is high code density and low power consumption. So this ARM7 supports high code density and a low power consumption. In this instruction, data were both in the same memory. So ARM7 uses von Neumann architecture. What is von Neumann architecture? Both data and instructions are available in the same memory. Then ARM9. So it is backward compatible with the ARM7. Whatever the features ARM7 is having, it is compatible with ARM9. ARM9 is backward compatible with ARM7, but it has 5 pipeline stages. They are fetch, decode, and execute, already there in ARM7. 2 more stages are there, memory stage and a write stage. So what is memory stage? So in this stage, the memory operands are read and written from the memory or to the memory that is present in the instruction. The data from the memory is, we can read or write. The data from the memory to the memory we can read or write. So that stage is called as a memory stage. And it has got one more stage called as a write stage. So in this stage, the fetched value is written back to the register present in the instruction. So what is the register present in the instruction? The fetched value is written back to the register. It is called as a write. So this feature we are not going to study. We are going to study only these three: fetch, decode, and execute. Memory and write back, because we are studying ARM7. ARM9 feature, it has got 2 more extra stages, memory and write. And separate instruction cache and separate data caches there. Since there are 2 memories used in ARM9, so it is hardware architecture. And ARM10, all backward compatible with ARM9. All ARM9 features are there in ARM10, but there are 6 stages are involved. They are fetch, issue. There is one more stage here: issue, decode, execute, memory, and a write. Next, we'll study the elements of data core model. So here, see, now we are going to study ARM data flow model. So in ARM data flow model, we have 8 elements: instruction decoder, register file, sign extend hardware, MAC unit, ALE unit, barrel shifter, address register, and incrementer. So once you see the diagram, you can remember all these elements. Sometimes they'll ask you list the elements of ARM data flow model. So you have to list all these 8 elements. How many? 8 elements are there. This is the diagram of ARM data flow model. So you can see all the elements, whatever I explained in the previous slide: instruction decoder, sign extend, register file, barrel shifter, MAC, ALU, address register, incrementer. So see here, 1, 2, 3, 4, 5, 6, 7, and 8 elements are there in a ARM data flow model. So here you can check the direction here. Data is coming towards the sign extend. Instruction is going to instruction decoder. From the sign extend, the data is stored in register file. And from register file, 2 buses are coming, the bus A and bus B. So the bus A, the content is available in register RN. From the bus B, the content is available in register RM. The RM content goes to barrel shifter. RM is called as second operand. RN is the first operand. The content of the RN goes to ALU. The content of RM also goes to ALU, but it goes via barrel shifter. So the result of the barrel shifter is marked as N. So you can check here, register file has 2 buses, A bus and a B bus. A bus, the registry used is RN. B bus, the registry used is RM, R suffix M. and RM goes to barrel shifter. After barrel shifter, RM becomes N and Rn remains same, and these two comes to ALU. And after the ALU, the result goes back to register file. It is marked here as result and RD. And from the address register, so it comes out. And the register file, one more line is coming as a address. And address register goes to incrementer. And incrementer comes back to register. This is the way of drawing the ARM core data flow model. Now we'll study one by one what is the function of each elements, 8 elements in a ARM core data flow model. The first one is instruction decoder. So look at the diagram here. This is the instruction decoder. So what is the function of this instruction decoder? We'll study now. The diagram is shown in the right side here and it is marked with the oval red line. It means we are explaining, I am going to explain this instruction decoder. So decoder means what? It decodes the instruction. So it translates the instruction before they are executed. We write the program using the assembly language or a C language. So before execution, the instruction must be translated from the assembly language into machine language. So the instruction decoder converts the instruction from assembly language to machine code. So that is done by the instruction decoder. Very important block. So without translating, you cannot execute the instruction. The programmer, write the program in assembly language. So the assembly language, it is a human understandable language. The computer cannot understand the assembly language or a high language. So it understands only the machine language. So we should convert the assembly language into machine language. That work is done by the instruction decoder. Each instruction executed belongs to particular instruction set. So each instruction executed, it belongs to a particular group of instruction set and it decodes and sequence all the ARM and thumb instruction. So I told the ARM supports the ARM instruction set as well as a thumb instruction set. The instruction decoder decodes the ARM instruction as well as the thumb instruction. If you give the ARM instruction, it decodes the ARM instruction. If you give the thumb instruction, it decodes the thumb instruction. Next block here I have marked as register file. The heading is register file. So the register file here I have written R0 to R15. It means there are registers starting from R0, R1, R2, R3, R4 up to R15. Total 16 registers are available in a register file. The data items are placed in register file. Data is stored in register file and instruction, it is decoded in the instruction decoder. And this registry is called as a storage bank because it is used to store the data. The storage bank is made up of 32-bit register. All the registers we used here are 32-bit register. Most of the instruction treat the register as holding signed and unsigned 32-bit values. So what you are looking here, it is a register file containing 16 registers. All the register size is 32-bit register. Remember, the size of the register is 32-bit. It acts as a storage bank because it stores the data. And most of the instructions treat the register holding the signed and unsigned 32-bit value. It holds 32-bit signed number or unsigned number. The two source registers Rn and Rm. See the previous diagram. Here we have used Rn and Rm. So the two registers are used. The same register I am showing here. The two source register Rn and Rm and a single destination register Rd. So you look in the diagram, there are three registers we can see, Rn, Rm and Rd. So Rn and Rm and what there is the two source, they are called as a source register and there is only one destination register, it is RD. D stands for destination, whereas N and M, they belongs to source register. Source operands are read from the register file using the internal buses A and B. So after reading the content of the register, then it must go on one bus. So one source operand goes on bus A and other source operand goes on bus B. So they are marked as bus A and bus B. This is about register file. So what are the things you need to remember in register file? It contains 16 registers, R0 to R15. The size of each register is 32-bit, and it acts as a storage bank because it stores the data, and the data is given to the two source registers Rn and Rm, and result is stored in destination register, and the source register contents, they are available on two buses A and B. So the next oval marked is sign extend. So what is the use of this sign extend? The register holds signed and unsigned 32-bit values we studied in the previous slide. The sign extend, it is a hardware. It is used to convert 8-bit or 16-bit number into 32-bit number. Suppose the data is, if you are feeding the data as 8-bit data, but what is the register size? 32-bit data. So the sign extend hardware, it converts 8-bit data to 32-bit. How it converts? The LSB, it retains the data. The remaining MSB, it makes the sign. If you are giving a positive number, it makes all the MSB bits are 0. And if you are giving the negative number, it makes all the MSB bits as 1. So it extends the sign of the data. If you are feeding the positive, so it gives the remaining bits as a 0 to make the number as a positive. If you are feeding the data as a negative, you are making the MSB bit as 1 to maintain the negative sign. So sign extend is a hardware which is used to convert 8-bit or 16-bit number into 32-bit numbers as they read from memory and placed in the register. See, the next diagram marked is MAC. So multiple and accumulate. MAC stands for multiple and accumulate. So this MAC unit computes the product of the two numbers and adds that product to the accumulator. So here multiply, as the name says, multiply and accumulate. It multiply the two operands. What are the operands coming? So the one operand is coming on bus A and one operand is coming on bus B. The two operands are available on A and B bus. These two operands are multiplied and the product of these two, A into B, it is added with the content of the accumulator. Here I have marked as ACC. It is added with the content of accumulator and result is stored in, once again, destination register. Next. It takes the register value Rn and Rm from A and B buses and computes the result. Data processing instruction write the result RD directly into the register file. So MAC stands for multiply and accumulate. Next diagram I have shown here is ALU. ALU stands for arithmetic and logical unit. It performs the arithmetic functions like addition, subtraction, multiplication, division, etc. And it performs the logical operations like AND, OR, NOT, XOR, XNOR, and so on. So it is used to perform both arithmetic and logical functions. ALU is used to perform arithmetic and logical operation. Data processing instruction write the result into RD directly to the register file after the multiplication or addition or AND, or after the operation is performed, the result is available in ALU. This result is given to RD, which is stored in a register file. The address broadcast on the address bus, the address is broadcasted on the address bus, and register RM can be pre-processed in parallel shifter before entering into the ALU. This point is very important. One operand which is there in RM is directly coming to ALU, and the second operand which is there in RM, it comes to ALU Not directly, it comes via barrel shifter. The barrel shifter, why it is used, I'll tell you in the next slide. Barrel shifter output is given to the ALU. Next is about the barrel shifter. So see the marked here as barrel shifter. So I told the ALU gets two data, one from directly from the RN and one from RM. It is pre-processed and given to the ALU. So what is this pre-processing and why it is required and what is the use of this barrel shifter? The barrel shifter can actually pre-process the data which can come from one of the source register. Barrel shifter can shift the data either to the left or to the right or even rotate the data before fetch to the ALU. Before giving the data to the ALU, one of the operand, that is operand RM, it is pre-processed. What are the pre-processing done by the barrel shifter? It shifts the data right or left or rotate. So these many functions are done by barrel shifter. Together, the barrel shifter and ALU can calculate the wide range of expressions and address. So with the help of this barrel shifter, so we pre-process the second operand and then given to the ALU. By doing this, the processor performance increases and the execution speed also increases. So all these function must be done by ALU. So before doing only, the barrel shifter is doing one of the operand pre-processing. So due to this, the performance increases. Next, about the address register. So address register stores the updated address. It stores the address and there is incrementer here. It is used to increment the address stored in the address register. Address register stores the address. So after the operation, the address must be, gets incremented. The incrementer increments the address stored in the address register. Incrementer updates the address register before the core reads or writes the next instruction value from the next sequential memory location. So suppose if the ALU is giving one data, so before giving the next data, the address must be incremented by one, the address must be incremented and the incrementation is done by the incrementer. So this is about the ARM core data flow model. So once again, you just look at all the elements, the purpose of instruction decoder to decode the instruction, sign extend to extend the sign of the bit. If you are giving 8-bit data, but register holds 32-bit, so 8-bit, 24 bits, what should be done? The sign is extended here. If the 8-bit data is positive, the 24, all remaining 24 bits are extended as a positive sign. If you are giving 16-bit data, 16-bit data is coming as LSB and remaining 16 MSB are extended as a sign. If it is positive, 0 is inserted into that. If it is negative, 1 are given in the MSB bits. Then barrel shifter pre-process the data. ALU does the arithmetic and logical operation. MAC multiplication and the result is stored in RD. And address register holds the address. Incrementer increments the address register content. Now we'll solve some multiple choice questions. Read the question properly. Evaluate the following statements and select the appropriate answer given from the choices below. Two choices are given. You should tell whether first one is true or second one is true or both are true. Von Neumann architecture shares the common memory for data and an instruction. So if you look at the diagram of von Neumann and Harvard once again, let us go back. See here in Harvard, you have separate program memory and separate data memory. In von Neumann architecture, there is a single memory. Now you can answer the question. So von Neumann architecture shares common memory for data and instruction. Harvard architecture has separate physical memory for data and instruction. So option is only one is true. First choice is true. Yes, it is true. Option B, only second is true. Yes, second is also true. Then option C, both 1 and 2 are true. Yes. So the answer is option C because Both 1 and 2 choices are correct. The option C is correct answer. Dash translates the instruction before they are executed. Among 8 blocks of ARM code data flow model, which block translates the instruction before executed? Is this register file? No. Register file acts as a storage bank. It holds the data. So option B, instruction decoder. Yes, it decodes the instruction. So it converts the assembly language into machine language. So option is B. Dash register can be alternatively pre-processed in a barrel shifter before it enters into the ALU. I told that ALU gets 2 operands, one operand from Rn and one operand from Rm. Rn goes directly to the ALU. So which is the answer here? Rn. Option is wrong because Rn goes directly to the ALU. Rm, right option, because Rm goes to barrel shifter and pre-processing is done and the result becomes N and that is given to the ALU. ALU. Option C is wrong. Both register we cannot use. None of the two are wrong. So answer is option B. For load store instruction, the dash updates the address register before the code reads or writes the next register value from or to the next sequential memory location. So who among all 8 elements of data core model, who will increment the address? So the answer is options are ALU, MAC, address register, incrementer. ALU, no, it will not increment the address. It does arithmetic and logical operations. MAC, no, it performs multiplication between the 2 operands coming on A and B bus. So address register, it holds the address. Incrementer is the right option because it increments the address register content. Option is D. Data items are placed in dash, ALU, MAC, instruction decoder, register file. ALU, so data items are placed in ALU? No, ALU is used for performing arithmetic and logical operations. MAC is used to do the multiplication operation. So data items are not placed here. Instruction decoder is meant for converting the instruction into machine code. The option is register file because it acts as a storage bank. So data items are placed in a register file. The next question is, the following are the elements of ARM code data flow model. So you remember all the 8 elements of ARM code data flow model. Among 8 here, one is, which one is correct? So instruction decoder, register file, ALU, barrel shifter. Is this instruction decoder is there in ARM code data flow model diagram? Yes, it is there. Register file? Yes. ALU unit? It is there. Barrel shifter? It is there. Then which option is right? Only 1? No. 1 and 2? No. 1 and 3 and 4? No. Or last option is all. All the elements are present which are given in the question. So the right option is option D. ALU and MAC unit takes the register values dash and dash from A and B buses and computes the result. So you check the diagram. There are 2 buses available, A and B bus. A bus gets the data from one register, B bus gets the data from other register, and the registers are marked as RN and RM. You have to fill here. So is this RM? So from A, RM is coming? No. So option A is wrong. Option B, RM and RM both side? No. So A has different source operand register and B has different source operand register. Option B is wrong. Option C, both are RN? No, wrong. So option D is right. So RN is coming from A and RM is coming from B. So the right option is option D. So you can, these are the descriptive type of questions. So you can write what are the difference between von Neumann and Harvard architecture, list the different elements. Just they have asked to list it, not explain. List the different elements, sketch a neat ARM core data flow model, explain ARM core data. Sketching, you may get the question on sketching, you may get the question on ARM. If it is explain, you will get question for 10 marks. If it is sketch, it is for 5 marks. If it is list, it is for 5 marks. If it is difference, this question will be for 4 marks or a 5-mark question. Thank you. We will meet you soon in the next session.